The highlighted part. Okay, is this a branch, a node, or a loop? Branch. Very good. Okay, how about this one? It is a loop. Okay, so basically you already know what is the difference between branch, node, and loop. Okay, so there is a reminder here or a certain note that says two or more elements, okay, two or more elements are in series. Okay, take note of this one. This is so important. Okay, two or more elements are in series if they exclusively. When we say exclusively, what does that mean? When we say exclusively, what does that mean? We are exclusively dating. Okay, when they actually said that we are exclusively dating or we are exclusively together, hindi nag-share. Okay, very good. That's it. That's the okay. There is no third party. Okay, you have actually, if you have watched the recordings, I've mentioned there what we mean by exclusive. Okay, when we say we are exclusively like that, or we are exclusively on a certain situation, it means that you are only there. You and your partner only. Okay, there is no third party and all. Okay, there is no other woman. Okay, so there is no other thing involved rather than the two parties. Okay, so two or more elements are in series if they exclusively share a single node and consequently carry the same current. Okay, so if I am going to at least draw a two series resistors just like this one. So we have resistor 1 and resistor 2. So basically there is a certain node in between. Okay? So R1 and R2 in that certain situation are in series. Correct? So what if I have connected another resistor in here? Okay. So this is now my R3. Is R1 and R2 still in series? No. Very good. They are not because they are not on the situation that they just exclusively share that single node. There is now a third party. Very good. There is now another one which is sharing the same node. Okay, therefore R1 and R2 are no longer in series. Okay, now the second situation is two or more elements are in parallel if they are connected to the same two nodes and consequently have the same voltage across them. Okay, so it has been said here that two or more elements are in parallel if they are connected onto the same two nodes. Okay, same two nodes. So I'll give you an example. So I have one resistor here and one resistor here. So this is my R1 and this is my R2. By the way, do you know how to name nodes? Do you know how to name nodes? Have you learned on the certain uh, on a certain teaching there that on how to name nodes? Do you know how to name nodes? How can we actually label a certain node? Okay, according to the definition a while ago, that nodes are the points of intersection of branches, right? They are the point of connection of branches. So if we have this circuit here, the red one, okay, if we have the circuit here, we have how many nodes? How many nodes do we have? Hmm? How many nodes do we have? Two? Do we have just two? Basically, if we are going to label them corner by corner or by intersection, we have four, right? So we have this node, this node, and this node. But if we are going to name it or if we are going to label them, we have just two. Okay, we have just two. So how to name them? So we can start on whatever or whichever node you wanted to start. Okay, we can start right here. Okay, right here. We can also start right here or right here or right here. Okay, so it depends on you. It depends on you whether you wanted, whether or whichever node you wanted to start labeling. Okay, so as for me, I will start on the first one, this node. Okay, so you can at least label them based on your discretion. If you wanted to label them as node X, node Y, node Z, node A, node B, node 1, node 2, whatever it is, okay, you can at least label them whatever name you wanted. Okay, so I will just label the first node as node A. Okay, so this is my node A. Next node that I'm going to at least name is this node. Okay, this node. So if I'm going to name this node, what is the name of this node? Okay, remember this one. If your node, let's say for example, this node A, okay, going to the second node, if there is an intervening element, your node name must be changed. Okay, so if it is A, this should be B, if and only if there is an intervening element. Okay, if there is an intervening element. But if there is no intervening element, it means that the name of your node here remains the same on your node in here. Did you get it? Okay, so if I would label this one, and this is again node A, correct? So if this is my node A, and I'll be going onto this node, what is now the name of this node? Node B. Very good. So this is now node B. What about this node? The last node. What is the name of the last node? Still B. Very good. So it is still B. So as you can see, we have already named those nodes. Okay? And if we are going back onto the second reminder, the two or more elements are in parallel if they are connected to the same two nodes. Okay? If we are going to take a look at R1. Okay? Take a look at R1. R1 is in what node? R1 is connected in what node? A and B. What about R2? What about R2? A and B as well, right? Is the node or is the requirement has been satisfied? Yes. Therefore, R1 and R2 are in what connection? Parallel. Very good. Okay. So we have now, actually, I have a certain analogy when it comes to series and parallel connection. When it comes to series connection, you have your boyfriends, right? Do you have your boyfriends? Or do you know someone who have maybe your mom and your dad, your siblings with their boyfriends, with their girlfriends and all? Okay, couple. Okay, you know a couple. So if two couples, or I mean a single couple, or couples, okay, if couples are holding their hands together, okay, it means that the left hand of the boy is holding the right hand of the girl. Basically, that situation is a series situation. Okay, that is what we call the single holding hands or the single hand to hand connection. Okay, series connection is a single hand to hand connection wherein two elements or wherein the boy, which is basically R1, and the girl, which is basically R2, is holding their hands together. Okay, they hold their hands together. Okay, when it comes comes to couples, when it comes to a certain relationship, third party is not allowed. Correct? Third party is not allowed. Always remember that. We can just say that two elements are in series if they exclusively share a single node. Okay. Now we go back onto the same couples. Okay. Have you already seen a couple that is standing, or maybe that, yeah, standing in front of each other? They are standing in front of each other, and they are holding each other's both hands. Okay, it means that the boy's right hand is holding the girl's left hand, and the boy's left hand is actually holding the girl's right hand. Okay, they are holding each other's hand. So it is what we call the double hand-to-hand connection. When we say double hand-to-hand connection, that is the parallel connection. It means, okay, R1, which is the boy, and R2, which is the girl, they are both holding their hands, or they are both connected onto the same two connection. Are we clear about that? Did you get the analogy? You get the analogy? Okay. So let us now go on to the conditions of resistors in series and resistors in parallel. Okay? So again, elements are in series when they are chain connected or connected sequentially. When we say sequentially, it is on a sequel. Okay? When we say on a sequel, or on this movie is a sequel. When we say it's a sequel, it is in a chronological order, right? It is in order. They are connected end to end. So if you have a bike, okay, the bike has a chain, and those chains are connected in series, right? Christmas lights are connected in series as well. Okay, so when we say resistors in series, we have different conditions. Okay, so on those different conditions, just like the equivalent resistance that we are pertaining to, the equivalent resistances, or what we call the total resistance. In other books, equivalent resistance is also called as the total resistance. When you are asked what is the equivalent resistance or what is the total resistance of a certain circuit, it means that they are asking about the equivalent resistance of the whole setup. Okay? So when it comes to the equivalent resistance of any number of resistors, it means any number of resistors that are connected in series, either they are 2, 3, 4, 5, 1,000, 1,000,000, of any number of resistors that is connected in series, okay, only in series, okay, only in series, it is the sum of the individual resistances. So for example, if you have two resistors or three resistors in series, in order to get the total resistance or the equivalent resistance, you just need to add them all. Okay? So let's say, for example, in this circuit, you have R1 and R2. So let's say, for example, R1 is 1 ohm and R2 is 2 ohm. What is now the total resistance of the circuit? 3. Very good. Okay, so just like that, it's very easy. It's just like you are on grade 1, so you just need to add. Okay, you just need to add in order to at least get for the equivalent resistances. Okay, now when it comes to the current, the voltage, and the power, okay, it has a certain condition as well. Okay, for the current, okay, when it comes to series, current is always constant. Okay, current is always constant. When I say current is always constant, it doesn't change. Okay, so let's say, for example, okay, just pretend or just imagine that I have 1 liter of water. Okay, 1 liter of water, and that 1 liter of water is my current. Okay, so of course, when I start this circuit, that 1 liter of water will flow from here to here to here, and it will actually energize your R1. It's still 1 liter, correct? So pretend that the whole circuit is a canal, right? Or is a canal of water, or it is something, a penstock. Okay, it's a penstock. So if you are going to trace the water from flowing to the initial part of the circuit up until the end, okay, the 1 liter of water is always 1 liter, correct? It will be 1 liter up until it flows throughout the circuit. Can you see it? So, or can you imagine it? That's why in series connection, our current is always constant. It means that your total current is equal to the current dissipated on R1 and also equal to the current dissipated on R2. Okay? Next, when it comes to voltage in series connection, voltage is additive. What do we mean by that? Okay, so if we have a total voltage of 12 volts, okay, you have a total voltage of 12 volts, and that 12 volts actually supplies the whole circuit. What will happen on our circuit then? Okay, so if 12 volts will come out here in, R1 will be getting a part, okay, R1 will be getting a part of that 12 volts that R1 needs in order for it to start correctly, or in order for it to start properly. Okay, then upon getting a part of the 12 volts, R2 will have the other part. Okay, ma'am, what if we have another R3 in here? Okay, actually, all of those elements that are in the circuit, okay, they are going to divide the whole 12 volts in order for each element to start properly. Okay, so they are going to get a part of that 12 volts in order for each element to start properly, depending on their value. Okay, depending on their value. Take note of that. It always depends on their value. Okay, next. So just remember, the higher the resistance, the higher the voltage. Okay, the higher the resistance or the higher the value of your resistor, the higher the voltage that must be dissipated on that certain resistor. Okay, did you get it? Question so far? Question so far? Is everything clear so far? Okay. Next we go on to the power. So when it comes to power, okay, whatever is the connection, either series or either in parallel, power is always additive. What do we mean by that? We need to get to at least get the power dissipated for R1 and the power dissipated for R2 and the power dissipated for R3 in order for you to get the total power. Okay, what is again the formula for power? What is the formula for power? Anyone? Power is equal to what? Voltage multiplied by the current. Very good. Okay? So power is your power is equal to your voltage multiplied by your current. Therefore, your total power can also be determined by the total power is equal to the total voltage multiplied by your total current. So if you already have the value for your total voltage and if you already have your value for the total current, you can at least get for the total power. You just need to multiply them. No need to get for the individual power dissipated on each element. Okay? Next, we have the resistors in parallel. So elements in parallel are connected to the same pair of terminals as I've discussed a while ago. So we have also the equivalent resistance of two parallel resistors. So we have here the three equations. Okay, the first equation or the first formula, this one, the upper part, this is the formula that is only intended or only applied if you are or if you have two resistors in parallel. Okay? two resistors in parallel. So in order for you to get the equivalent resistance of two resistors in parallel, that is equal to the product of their resistances divided by their sum. It is the product over sum. So if you have this circuit, you have your R1, okay, and you have your R2, basically, you can get the total resistance of R1 and R2 by simply getting the product of R1 over R1 and R2 divided by the sum of R1 and R2. Okay, you can at least do this formula, or you can at least get for the equivalent resistances of R1 and R2 through this formula. Okay, next we have also this. We also have this formula. So there's a formula here that R total, or the equivalent resistance of parallel resistors, okay, multiple resistors in parallel, either 2, 3, 4, 5, 6, and so on and so forth, for as long as they are in parallel, you can at least use this formula. That RT is equal to the quantity of 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R, and so on and so forth, raised to negative 1. Actually, I prefer the second formula rather than the third formula, because the second formula is much better to, or yeah, it is much better to type on the calculator rather than on the third one. But of course, if you also prefer the third one, you can at least apply this one. Okay? So this is now the formula for your equivalent resistance when it comes to parallel connected resistors. Again, the first formula is just applicable if you have only two, okay? Only two resistors in parallel. Okay? The second formula as well as the third formula is applicable whether you have two, three, or multiple resistors in parallel. Did you get it? Did you get it, my dear EE21S1? Okay. Next, let us now proceed on to the conditions when it comes to voltage, current, and power. So when it comes to voltage, it is somehow the opposite of the condition in series. So when it comes to series connection, our voltage is additive, right? But when it comes to parallel connection, our voltage is constant. It means that the total voltage that is given by our voltage source in here is also the same voltage that would be given on R1, and also the same voltage that would be given on R2. Okay? So it means if it is 12 volts, R1 will also receive 12 volts, as well as R2 will also receive 12 volts when it comes to parallel connection. Okay? Next, when it comes to your current, okay, or when it comes to your total current now when it comes to your parallel connected series, parallel connected circuit, it is always additive. Why is it additive? Okay, so again, imagine that our current is 1 liter of water. Okay, so let's just imagine that it is 1 liter of water. So upon flowing from the source, okay, of our 1 liter of water, it will come into this node, correct? It will come up onto this node. So what will happen to our 1 liter of water? So imagine that this circuit is a canal of water, or a certain penstock that a certain water can flow. Okay? A certain water can flow. So if our water flows onto this corner, or onto this node, onto this connection, what will happen on your water? What will happen on your water? Will it only flow onto one side? It will go on separate ways. Very good. Okay? It will go on to two separate ways. It's either some part will go in here and some part will go in there. Correct? So your water, or or your current, your total current will be divided. Okay, it will be divided. Not necessarily that it will be divided into two, or it will be divided equally. It depends on the value of your resistor that is being supplied. Okay, so it's either maybe 70% of your water will come here and the other 30% will come here. Okay, so the 70% now will be flowing into here, okay, meeting the other 30% here, going back as 100% total. Okay, did you get it? Did you get? That's why our current is now additive. It means that the current dissipated in R1 plus the current dissipated in R2 and the current dissipated on all the resistors in parallel, when you add them all, that is the total current. Okay? Did you get it? Did you get the idea? Okay. Now, when it comes to power, as I've said a while ago, whatever is the connection, either series, either parallel, series, parallel, whatever is the connection, delta to Y, our power is always it is always additive. Okay? Or you can at least use that the total power, okay, your total power or PT is equal to your total voltage multiplied by your total current. Okay? Now, we have what we call voltage divider rule. Okay, voltage divider rule is applicable in what connection? Where voltage divider rule is applicable? In what connection it is applicable? The voltage divider rule. When we say voltage divider rule, your voltage is being divided to your resistances. So where it is applicable? In what connection? In where? In series. Very good. So our voltage divider rule is only applicable in series resistances. Take note of this one. VDR or voltage divider rule is only applicable in resistor in series. Okay? So the formula for our voltage divider rule, if we have two resistors in series, okay? So let's say for example, you have two resistors in series. Okay, so this is your R1 and this is your R2. Okay, so you are going to get for your V1 and for your V2. Correct? So if you are going to get for V1, you will use this formula. Okay, this formula that V1 is equal to your R1 over R1 plus R2 multiplied by V, wherein V here is not necessarily the total voltage in the circuit. Okay, it is not, again, V here is not necessarily the total voltage in the whole circuit. V is the voltage that is being divided by the two resistors. Okay? So if you have, later on, if you will have your series and parallel connection, your V, okay, your V is the voltage that is being divided by the two resistors that you are going to get the voltage drop. Okay, so let's say for example, in this circuit, since this is just a very simple circuit and you have your total voltage in here, let's say this is 12 volts, okay, it means that your V, the V that you are going to use here is 12 volts since they are just two resistors. But if you have a certain series and parallel connected circuit or a series parallel circuit, later on it is not necessarily that V is also the total voltage. It depends on the situation. Okay? It depends on the situation. Just always remember that V here, okay, V here is the voltage being divided on those two resistors. Did you get it? Is it clear? Are we clear about that? Are we clear? Okay. Voltage divider rule. Is it applicable if you have three or more resistors? Yeah, it is. Your voltage divider rule can also be implemented if you have three or more resistors. You can at least use this formula, the formula below, this one. Okay. So if you have, let's say you have five resistors in series and you are going to get the voltage across the fifth resistor, so that is a V5. So definitely that is the resistance of your fifth resistor all over the total resistances, or that is R1 plus R2 plus R3 plus R4 plus R5 multiplied by the voltage being divided. Okay, did you get it? So you can at least use this formula if you have more than two resistors in series. Okay, any other more question? Any other more question, clarification, comments? Okay, so if you don't have, let us now proceed to the current divider rule. So we have now the current divider rule. So current divider rule is only applicable in parallel connection. Okay, so parallel connected resistors. So we can at least implement the current divider rule because in parallel, our current is additive and our voltage is constant. Okay, so you could at least use this one wherein if in order for you to get your I1, that is R2 over R1 plus R2. So maybe we could at least demonstrate the circuit herein. So if you have your R1 parallel with your R2 and you have your source in here, okay, so this will be your voltage total and you have your total current in here, correct? Okay, so in order for you to get for your I1 and in order for you to get for your I2, so you need to at least get for I1, get R2, the value of your R2, the value of your resistance 2, all over the value of your resistance 1 plus the value of your resistance 2, multiplied by I, wherein I here is the current being divided across the two resistors, okay, or between the two resistors. So in this setup, our I is the I total. Okay, so if it is 2 amperes, 3 amperes, so that would be herein. Okay, just plug it in and then just evaluate the whole setup. Then you will get the I1. And as well as for I2, so in order for you to get for I2, so that would be just equal to R1 all over R1 plus R2 multiplied by the current being divided across or between those two resistors. Did you get the current divider rule? Did you get it? Do I have some students? It seems you're asleep. Okay, so let us now have our example. Let me draw a certain circuit so that we can at least have it as an example. this should be our R1. This is our R2 and this is our R3. Okay, so we need to find for the total resistance, for the total current, for your I1 maybe, I2, I3, for your V1, V2, V3, and for the total power. Okay. So as you can see on the circuit, which is the first parameter that we can at least get based on the circuit, based on the given, which is the first parameter that we can get. Okay, total resistance. Very good. So how can we get for the total resistance? Of course, we are going to evaluate our circuit. So what is the connection between R1 and R2? Is R1 and R2 in series? Are they? What is again our condition for series connection? Are they in parallel? So let us label the node. Okay, let us label the node so that we can at least determine or analyze our circuit. So we have 1, 2, 3, 4, 5, 6. Okay, so this is the first node, this is the second node, and this is the third node. This is the fourth one, fifth, and the sixth. So let us now name the nodes. Let me just fix my pen. It's not working. Okay. Okay, so let us now label our node. So this will be my node A. Okay, so this second node herein is now my node B, correct? And this is now again my node B. This is my node C, and this is C as well, and this is C. Okay, so let's go back to my question a while ago. What is the connection between R1 and R2? What is the connection between R1 and R2? Or shall I rephrase my question? Is R1 and R2 in series? No. Is R1 and R2 in parallel? No as well. Therefore, R1 and R2 don't have any connection at all. Okay? They don't have any connection at all. How about R1 and R3? Is R1 and R3 in series? No. Is R1 and R3 in parallel? No as well. Therefore, R1 and R3 don't have any connection at all. Correct? What about R2 and R3? R2 and R3. Okay? Let's take a look at R2 and R3. Are they in series? No. Are they in parallel? They are. Very good. Okay? So R2 and R3 are in parallel because R2 is connected at node B and C as well as R3 is connected at node B and C. Okay? So therefore, we can get their total resistance, the total resistance of R2 and R3. So let us just label, label the total resistance of the two resistor as R23. So R23, okay, now is equal to the product over sum, Correct? When we are actually getting the total resistance or the equivalent resistance of two parallel resistors, we are going to implement the product over sum. Okay? So therefore, this will be R2 multiplied by your R3 all over your R2 plus R3. So this will be now 2 multiplied by 3 all over your 2 plus 3. So this will be 2 times 3, 6 all over 5. So this will be 6 over 5 ohms. Correct? Correct me if I'm wrong. Is this correct? Okay. So therefore, we have now, or we can now reduce our circuit into this kind. Okay, so you have now your R1 here and you have your R23 there. So this will be your R1 and this will be your R23. So in order to get for your total resistance, what is the connection between R1 and R23? Can you still see the PowerPoint? No. So let me just share it again. But you can hear me. Basically, you can hear me. Okay. So let me just share it again. There's just a problem on the connection, I think. Okay. Can you now see it? Okay, so going back to my question, what is the connection between R1 and R23 now? They are in what connection? They are in series connection. Very good. Therefore, in order for me to get the total resistance of the whole circuit, I just need to add up my R1 and R23. So therefore, this will be R1 plus R23, or this will be 1 ohm plus 6 over 5 ohms. So basically, this is 5 over 5. We have 11 over 5. Am I correct? So 11 over 5 ohms. So that would be your total resistance now. So we already got the total resistance, which is 11 over 5. So what is next? What is the next parameter that we can obtain? What is the next parameter that we can obtain? The I total. Very good. We can now get for the I total. So we know that we have the Ohm's law. Correct? We have the Ohm's law that our voltage, our voltage is equal to our current multiplied by the resistance. So therefore, in order to get for your current, you have to divide your total voltage all over your total resistance in order to get for your total current. So we have a total voltage of 12 volts, okay, and a total resistance of 11 over 5 ohms, correct? So therefore, this is 60 over 11 amperes. Am I correct? I don't have the calculator, so uh, I'm using, I'm just using the manual, okay, my mind to at least compute this one. Am I correct? This is 60 over 11. 12 times 5 is 60 over 11 amperes. Okay. So this will be now our total resistance. So what's next that we can get after the total current and the total resistance? What's next? We can now get for I1, I2, and I3, correct? So if we are going to observe this circuit here, this one, okay, So we know that this is a full series connection circuit. Okay, a full series connected circuit. This one, the simple one. Okay, the reduced circuit. Therefore, if we are going back onto the conditions of series circuit, we know that in series connection, our current is constant. Correct? Our current is constant. Therefore, I can say that my I1 and my I23 is equal to my I total. Correct? That my I total, okay, I total is equal to my I1 and also equal to my I23. Therefore, my I1 is equal to my I total, which is also equal to 60 over 11 amperes. Do you agree? Do you agree? Okay, how about I2 and I3? How can we get for I2 and I3? Okay, so if we are going to observe now the whole setup or the whole circuit, so if your I total, which is 60 over 11, will be here, okay, it will come onto this corner. It will be divided into R3 and to R2. So what certain formula that we can implement in order to get how much current will be for R2 and how much current will be for R3? What formula? Is it the voltage over the resistance? Can we do that? Can we Do we already know the voltage on R2 and R3? I think no. Because 12 volts, okay, we cannot say that 12 volts is also, the total voltage in here is also the voltage in here and also the voltage in here. Because there is an intervening element in here, wherein when you actually draw or when you actually started your circuit, R1 would get first a part of your 12 volts before it actually gives to R2 and R3. The voltage in R2 and R3 are the same, but you don't know what part of 12 volts is your voltage on R2 and R3. Are you getting my point? Okay, very good, John. We can at least use the current divider rule. Okay, we can use the current divider rule. So as I said a while ago, if we have 60 over 11 that flows in this part of the circuit, and it will actually come up onto this corner of your circuit, your 60 over 11 will be divided accordingly to your R3 and to your R2. Correct? So you can at least use the CDR or the current divider rule. Okay, so by current divider rule or by our CDR, okay, we know that our I2 now is equal to your R3 all over your R2 plus R3 multiplied by the current being divided. Correct? So therefore, this will be your 3 ohms all over your 2 ohms plus 3 ohms divided, multiplied by 60 over 11. Correct? So this will be 180 over 555. Or if you are going to reduce it in its lowest term, that is how many? That is 180 divided by 5. So you will have 9. 9. So you have 36. 36 over 11. Am I correct? That is 3 times 60 is 180. 180. So this is 36 over 11. Use your calculators, please. I know you have your calculators. Okay. So this will be now equal to 36 over 11. Yeah. 36 over 11 amperes. Okay? So let us now get for our I3. So our I3 now is equal to your R2 all over your R2 plus R3 multiplied by I. So this will be equal to 2 all over your 2 plus 3 multiplied by 60 over 11. So this will be 120 over 55. Okay, so that would be 24 over 11 amperes. Correct? So we have now the value for I1, I2, and I3. Can we now get for the value of your V1, V2, and V3? Can we now get for the value of your V1, V2, and V3? Yes, okay. So for V1, okay, basically we know the Ohm's law V is equal to IR. So in order for us to get for V1, so that is I1 multiplied by R1. Correct? So I1 is equal to your 60 over 11 amperes multiplied by your R1, which is 1 ohm. Therefore, your voltage is 60 over 11 volts. Okay? Now, your V2 is equal to your I2 multiplied by your R2. So, therefore, your I2 is equal to, what is your I2? Your I2 again is 36 over 11. So, you have your 36 over 11 amperes multiplied by your 2 ohms. Sorry, this is ohms. 2 ohms. So, therefore, this is equal to 72 over 11 volts. Now, your V3 is equal to your I3 R3. Okay, so you have your I3, which is 24 over 11 amperes multiplied by your R3, which is 3 ohms. Okay, so this will be now 72 over 11 volts as well. Okay, now my question is, V1 is 60 over 11 volts. Why is V2 and V3 equal? Why they are both 72 over 11 volts? Hmm? Why is the two voltage V2 and V3 equal with each other? Because they are parallel. Very good, John. Okay? So because they are parallel. So as you can see in here, okay, your R1 will get 60 over 11, okay, 60 over 11 volts first. And the other part, which is the 72 over 11, will be for R2 and R3 since they are connected in parallel. And according to the parallel condition, that your voltage is constant. Okay, since R2 and R3 are in parallel, therefore, they must have the same voltage. Correct? Did you remember it? Can you remember it? I hope you do. Are you still following, my dear EE21S1? Okay. So let us now proceed on to the last part of the problem. That is by getting the total power. So total power now is equal to your total voltage multiplied by your total current. So therefore, this will be equal to 12 volts multiplied by 60 over 11 amperes. So this will be now equal to 6 times 12, so this is 720. So this will be 720 over 11 watts. Is that correct? Okay, so that would be the answers for this circuit. Any question? Question, clarification? Okay, so I hope you do now understand what is the difference between a series connection and a parallel connected resistors in a circuit. And then, do you have any more questions regarding the other topics? Any other questions, queries, clarification if you have any? Are you learning so far? Are you learning? I just can see Paul, John, Lance, Elvin, Ryan, Hens, and Andrea, as well as Gerald. Where are the others? Where is Mary? Where is Aira? I think Aira is already not around. Where is she? Where is Marvin? Joshua? Where is Treb and Christopher? Did you understand the discussion today? Any question? Question before we wrap things up? Before we actually end the conference for today? Okay, so if you don't have any questions, I have a question. Okay, so what are your key takeaways in today's discussion? Will you at least have a brief sharing or a brief summary on what did you learn on today's discussion? What are your realizations and all? PowerPoint will be uploaded on your group chat as well as on the Canvas. So what are your key takeaways in today's discussion? Will you type your answer on the chat box? Do not just copy and paste what your other classmates have said. How to analyze a circuit and how to solve the parameters. Okay. What else? When it comes to relationship, it should be a series connection. Okay. Maybe that's a good realization then. What else? How to differentiate the circuit connections. Okay, you can now you now know how to differentiate the series from parallel connection, right? I learned how to analyze the series and parallel resistor connection. Know the difference between CDR, okay, the CDR and a VDR when it would be used. Okay, so that's a good learning, Andrea. Okay, how to differentiate circuit connections and their conditions, and also how to apply the VDR and CDR. Okay, formulas that are applicable for series and applicable for parallel. Okay, so take note, guys. I just wanted to remind you that this topic on your circuits one will be very significant or will be very important, very essential, very imperative. Okay, that's also the synonym of important. This is very important when it comes to your circuits too. So if you will pass, okay, if you will pass circuits one and will be on your circuits two by next semester, you will again encounter these conditions. Okay. So if I were you, take note of these conditions, bring these conditions on your circuits too, because these are very necessary. Well, up until your fifth year, up until you graduated, this is the fundamental of electric circuits. So you know how to differentiate, you know how to analyze or to evaluate at this circuits. You know what is the connection between these two resistors or between these two elements and all. Okay, so again, we also have the other connections, just like the delta connected and the Y connected. Okay, so I hope you also do remember how to at least evaluate those kinds of circuits. Okay, so if you have any more questions and you are just ashamed or maybe you are just hesitating to ask it right now, so please just message me on my messenger account or maybe on my email. Send me an email about your concern, about your queries, about your questions when it comes to our topics on on electric circuits. Maybe you could at least also give me a call. I have my number on to onto some parts of the modules. I think under the course, I think I didn't include it yet. Okay, so maybe you can just at least reach me on you can just reach me on my messenger account. Can I ask what would be the contents of our prelim exam? Okay, your prelim exam or final exam will be from the very start. Okay, just refer on your module when it comes to your topics. Okay, when it comes to the topics that is included on your examination. Okay, so there won't be any topics that is not discussed which will be included on your examinations. All topics that is on your or all the contents of your examinations are the topics that is on your modules. This Friday, uh huh. Mm-hmm.